Today what we are going to do is we are going to just look into what are the applications of an operational amplifier. Okay, the list is not exhaustive, there are other applications as well, but then these are some of the preliminary applications of OpAmp, and if we just do a lot of combination of these systems, we can actually put OpAmp into different use. Some of the applications probably we have already talked about a bit, okay, but not much in detail. Probably we'll just look into some mathematical calculation of these, okay. And out of them, I think inverting amplifier, non-inverting amplifier is something which is very much applicable, okay. And then the voltage follower, integrator and differentiator, and comparator. So whenever you are going to have a output which is 180-degree out of phase, okay, if we consider this, and if this is 180-degree out of phase, okay, then this is something which we call as the inverting terminal. So this is something which you already know, okay, and this is basically in phase, okay, this is in phase, okay. In voltage follower, what happens is we are basically going to have similar type of circuit, okay, and basically there is going to be a loop that is getting formed. In an integrator and a differentiator, maybe we can just try to have a square wave, okay, and convert them into a triangle wave. That can be the application of an integrator, okay, or we can have a triangular wave and we can actually convert them back to a square wave, and that is what is the differentiator is used for, okay. And then here what we do usually is compare two different voltage sources, okay. So based on this we have our discussion, and what we are going to do is we are going to start off with the inverting amplifier. In this particular section, please remember, probably we have to keep on drawing the OpAmp again and again, okay. So we need to just draw it and we need to do the modification as per the application. So the first part is inverting amplifier. So we'll start with inverting amplifier, okay. And before we really start with the topic, I guess we need to draw the circuit first, okay. So whenever you are going to draw the circuit for OpAmp, straight away just go for the symbol first, okay. And then of course you'll be basically having one output, so you can straight away draw this, okay. And then you have to take care of what you do with the inverting and the non-inverting terminal. Now you see the name suggests that it is basically an inverting amplifier, so the non-inverting part you can just ground it off, okay. So we just mechanically ground this, right. So this is your non-inverting part and this is the inverting terminal. So whatever changes we are going to do, we're going to do it in the inverting terminal, okay. So maybe we can just draw a resistor here, and this is basically nothing but an input resistor, okay. So it depends on what kind of application we are doing, but then most of the time we do have an input resistor. And we also need to remember the fact that an OpAmp usually has got an infinite input impedance, okay. So this is the input part, okay, and let's just complete the input part here. We will actually have a signal, okay, and let's say we are actually having an AC signal, and let's we mark this as V in. So that's the input part, okay. If we use an OpAmp, typically we actually need to give a feedback circuit, okay, and then this feedback circuit is again given via a resistor. So what we will do is we'll usually connect an output resistor, okay. So let's just draw an output resistor here. So probably we are going to use these kind of circuits again and again, okay. So this is usually your output resistor, okay. So I would suggest all of you to just practice it, okay. So this is your input resistor, this is your feedback resistor. Usually it's called as the feedback resistor, okay. We have the connection here, so I'll just make this points here, okay. And let me mark this point as point A, okay, this particular point. And then we have got the output, let's say, across this end. And now you know it's an inverting terminal because amplifier, because we have applied the input here, and the output that we are going to get is possibly going to be out of phase. Okay, so this is the basic diagram that most of the times we'll be drawing. Okay, and let me just make a simplified diagram of this. Okay, so what I'm going to do is probably I'm going to just take the same diagram. Okay, and then I'm just going to do certain modifications here. Okay, okay, just got doubled. So we have the V output here. So this is usually how you draw this circuit. Okay, now what I'm going to do is I'm going to just look into the polarity and everything else. Okay, so plus minus, please remember this is inverting amplifier, because whatever is the input, the output would be 180-degree out of phase. Okay, so this is your input. So that means if you are applying an input, you definitely have an input current, and let's say I in is the input current. Okay, and you know the op-amp has got infinite input impedance, so that means the current cannot flow across this. Whatever current is here, the same current will also flow through F. So maybe we can just mark it this way. This is the current that flows through F. So this would be IF. Okay. And since the input impedance is very high, that means the current cannot flow across this. Whatever is the current in this section, same will be the current in this section. So it is more or less just like a series connection. Okay, so maybe we can just apply some polarity here. And since no current can flow here, it can be considered as virtually at grounded. You know, there is a term which we call as virtual ground. Okay, virtual ground means it is basically having zero voltage at that particular point. Okay, so we have this particular circuit diagram, and you just need to remember this. Okay, so maybe I just can just clean it a bit more. Okay, so I will just put input across this, and I'll just write down R in here. Okay, so this is the circuit for the inverting amplifier that you need to draw before we can actually analyze. Okay, so let's see what are the different things that we have. First term is V input. Okay, and V input is basically applied through R in, right? So V input is applied through R in. So this is something which we already see here. Okay, and the output feedback. So in order to keep the amplifier moving, we have to take a part of the output and feed it back to the input here. Okay, so we basically apply this through RF, output feedback through RF. So F basically stands for feedback, IN stands for input. Okay, but then this RF will basically give you a negative feedback. Okay, through this RF we basically have got a negative feedback. I hope it's quite clear, because it's 180-degree out of phase. Okay, so negative, because never get confused here. Okay, it's important in op-amp. Out of phase with respect to input. Okay, so this is what we need to remember regarding this particular diagram. So whenever you're explaining inverting terminal, you have to draw this circuit and explain these parts. Okay, so you know, in general we can say that the input impedance is very high, right? The input impedance is very high, we already know. So what we can say is, since the input impedance is very high, So that simply means that whatever we have the current, okay, that means I1, or let's say I input, or the current to the input, okay. So let's write it down: current to the inverting input is equal to 0. This logic we are going to use again and again, so just make sure that you understand this, okay. So that means I input, okay, I input will entirely flow through Ri and Rf, will entirely will entirely flow through Ri, okay, and Rf. So the entire current will basically flow through these two circuits, or these two resistors, right? So let me just write it down: In input, and this will flow across R and Rf, right? So in general, what we can say is that this IF, whatever current is flowing through the resistor RF, is equal to the same current which is being applied in the input. So I'll just write it down as In. Okay. Now let's just define input. So let me just write down this. I want to just find out what is the input current. Okay, so this is a simple circuit analysis. Okay, so what will be the input I in? We have to know what is the voltage across R I in, right? So that means we can just simply write it down: what is the voltage, okay, across Ri, okay, divided by Ri. So you know current is equal to voltage by resistance. So if you know the voltage across Ri, divide by Ri, we can get it, right? So what is the voltage across Ri? That means whatever is the voltage on this side minus whatever is the voltage on this side. So you can see, we can just simply write it down as V in minus VA divided by Ri. So V in is this is the input voltage, and at this particular point the voltage is 0 because there is no current as such, right? Because it's a high, infinitely high impedance. So we can just simply write it down as V in minus 0 divided by Ri. So you can simply write it down as V in by Ri. Okay, so this is important. Okay, so please remember this: I is equal to 0 at A, and this is the logic that we have used. Okay, so that means at this point A there is no voltage drop, no voltage drop. Okay, so these are some of the important points. Then let's find out what is IF. Let's find out what is IF. So IF is nothing but voltage, right, across RF. Now across RF, and then we will divide it by whatever is the resistance, so that's RF. So if you take voltage across RF divided by RF, what is the voltage across RF? We have to take what is the voltage here and what is the voltage here. This particular point, the voltage is nothing but this V out, right? So we can just simply take it to be VA minus V out divided by RF. Okay, please understand the logic. If you understand it once, I think it should not be difficult. So it is again 0 minus V out divided by RF. So this is minus V out by RF. So we have got what is I in, what is IF, okay, and as per the definition, I in and IF must be equal. Okay, that's the same current that we are usually talking about, right? So since IF is equal to I in, what we can write is minus of V out divided by RF is equal to V in divided by Ri, right? And then from here we can actually write down what is V out by V in. V out by V in. So if we just do that, there is a minus sign. So I'll just write it down as minus of Rf divided by Ri. So if you take the ratio of the two resistances, you basically get V out by V in, okay? And V out by V in is nothing but, if you remember, we have discussed it before, this is written as ACL. And what is ACL? ACL is nothing but the voltage gain. Voltage gain. Okay, so this is important. Okay, and on top of that, if we just want to say that why there is a negative sign, okay, this negative sign, this implies 180-degree out of phase. So look here, if you want a very good output with respect to input, if you change the value of RF, so that means if we can just increase the value of this resistance, okay, let's say the resistance is high compared to this R in, we can actually get a very good voltage gain, a very good amplification factor. And this is what is inverting terminal is all about. Okay, so probably we'll just write down few points here, okay, but then when you write down in your exam, if you can remember this, all of these points are obvious, okay, whatever we have discussed, these are the points, okay. So let's just note down some points here, and then we can move ahead with one numerical to do, okay. So number one, the closed loop voltage gain, okay, is independent of the OpAmp's internal open loop voltage gain. So if you don't have any kind of feedback circuit, okay, that means we are basically talking about an open loop, okay. OpAmp's internal open loop voltage gain. So open loop voltage gain and closed loop voltage gain is something which we have already discussed, so please refer back to that, okay. So the closed loop voltage gain actually does not depend on that open loop voltage gain here in this particular case, okay. Inverting amplifier, okay, can be designed for unity, okay. So it means that if I really don't want to amplify the voltage, I can easily do it. It's very simple, right? If Rf is equal to Ri, okay, we can have A CL equal to -1. So I think this is quite obvious, okay. So if we take this Rf is equal to Ri, we can have the loop gain as just -1, because that's just the ratio between Rf and Ri, okay. So that kind of design is also possible to do. Next, now I am not interested in having a unity gain, I want to have more gain, so I can equally adjust it. So if Rf, just write it down, this in some multiple of Ri, okay, so Rf will be some multiple of Ri, so we can actually have the amplifier gain, okay, is constant. We'll have a constant amplifier gain. Please remember, you cannot have an infinite value of Rf compared to Ri because of the restrictions of the device, okay. It's not that you can have any value. Up to a certain limit, it will actually act under optimum condition, okay. So inverting amplifier, basically whenever we are using it, inverting amplifier provides constant voltage gain, okay. So it basically has this important application. Let's write down a problem, okay. Let's just try to solve it, okay. Determine the, I'll give you some problem to do, and in exam also probably will have some problems, okay. But then right now it's important that we understand how we use these formulas. It's not very difficult, okay. So determine the output voltage. So we can actually have a circuit, and based on that we can actually have an output voltage. Okay, so let me just have a circuit something like this. Okay, let me cut this off. So we have a circuit here. Okay, and probably I'll just not label RF and RI. You have to just, during exam you have to just understand this, the values. Okay, and then maybe we can just do it. So let's say we have got an input voltage of 2.5 millivolt. Okay, and then we have got Ri as 2 kilo ohm. Okay, and this is nothing but 200 kilo ohm. So you see RF is 100 times greater than Ri. Okay, we've got V and F and V out and V in. The question is, you have to determine what is V out, right? So when we talk about V out, we generally mean that V out divided by V in is equal to nothing but the gain, so ACL. So that means my aim is to find out V out, so I have to find out ACL into V in. So V in is already provided, it is 2.5 millivolt. Okay, I need to find out what is ACL. So we have just seen the formula now, and we are applying it to the inverting terminal here, so we have to put a minus sign. So I'll just put a minus here, and then you can just simply write down the formula as RF divided by RI. So we just take RF, both are in kilo ohm, so I don't really need to convert them into ohm, so this is fine. 200 kilo ohm, and ACL does not have any unit, you need to remember this. But you also need to remember that if this is, let's say, kilo ohm, or this is in mega ohm and this is in kilo ohm, definitely you need to do the conversions accordingly. Okay, both are in kilo ohm, so I'm not converting the units, so I'll just take this, and this would be nothing but 100. Okay, inverting terminal, so I'll put a minus sign. So in that way I can easily find out what is V out. Okay, so V out is equal to ACL, which is minus 100 into whatever is the input, 2.5. So in the question line itself, I'll just write down, answer line itself, I'll write down what is the unit, millivolt. Okay, and then you can just multiply it with 100 and then be divided by 10,000, and then you can do your conversions and convert it into volts. So 0.25 volts. So you see, this is a simple problem. You will be basically given a circuit, you have to find out what is the output voltage. You also get these kind of questions in entrance exam, and so you should be just clear with the formulas that we use. The formulas are different for inverting and non-inverting terminal. Let's going to look into the non-inverting terminal now. Okay, so if I ask you this question, this minus sign plays a very important role, so please don't miss out on that. Also, you need to note here that we have got just 2.5 millivolt as the input voltage. The output voltage is 0.25 volts, so it has amplified 100 times. Okay, so that's a huge amplification. So this is a value that is acceptable in general. Normal amplifier can actually have these kind of amplification factors. Okay.